All right, welcome to section 4.4, solving exponential and logarithmic equations with me, Mr. Hain. All right, guys, tray tables up in their upright position, seatbelts fastened. This is going to be a long one, but it's going to be awesome and full of amazing stuff that just happens when we explore exponential and logarithmic equations. So first, we got to take a look at the key. The key to solving exponential equations is twofold. The first one is setting the bases equal to each other. See, if the bases are equal to each other, then we know that the exponents have to equal each other. In this case, x equals y. Yep. Therefore, if the bases are equal, the exponents are equal, and we can solve for an unknown in the exponent. Let's take a look at some examples. The first one here, 2 to the 3x minus 8 is equal to 16. Now, this makes me feel a little bit interesting because I know that I can rewrite 16 with 2 as a base. It's 2 to the 4th. So now I know that the bases are equal when I rewrite the equation, and that lets me set the exponents equal to each other, which gives me a simple two-step equation. 3x minus 8 is equal to 4. Move the 8 to the other side using the inverse, and then use the inverse operation with the coefficient of x. Divide by 3. X is equal to 4. So let's take a look at a different example. This is a little bit deeper. You see the 27 and 9 also make me feel a little bit odd. That's because I know I can rewrite both of them with 3 as a base. So by rewriting each of them with 3 as a base, you see that I have two equations that I can set equal to each other. The exponents I can set equal to each other. I'm going to distribute here, which gives me 3 times x is 3x. 3 times 3 is 9. 2 times x is 2x, and 2 times negative 1 is negative 2. Here I have a multi-step equation, but again, this is something that you guys should know how to do. I'm going to move the x's to one side by moving the smaller x variable coefficient. I'm going to move the numbers, the constants, to one side. It leaves me with x is equal to negative 11. Sweet. All right, so as long as we can set the bases or make the bases the same, we can solve exponential equations, equations with a variable in the exponent. All right, why don't you try these? First one, checkpoint 1A, I'm going to pause the video. I'll be right here when you come back. Why don't you pause the video and check your answer and your steps to see if you get it. All right, and we're back. Let's check that work. All right, so rewrite 125 as 5 to the third power. Set the exponents equal to each other. Inverse operations, and yes, x equals 3. If you got that, man, give yourself a pat on the back. All right, let's take a look at the second example. Go ahead and pause the video here and take a moment to work that example out on your own. I'll be back when you're done with your work. All right, yes, 8 and 4 can be written with 2 as a base. We're going to distribute those exponents, set the exponents equal to each other, move the x's, smaller x first, smaller x coefficient first, then the constants to the other side, and x is equal to negative 12. Yes, okay, so this was the simple cases. But now we got to think about what about cases that we cannot rewrite the exponents. So here we see a case here, 4 to the x is equal to 15. Now, if that was 16, golden, but it's not. So here we have to apply the natural logarithm to solve exponential equations, or applying the power rule in reverse, or plugging for the win, if you've been following my other videos. So we have an exponent in the, or a variable in the exponent, which again, now we need another tool, which is a natural log. So I'm going to take the ln of both sides. Now, this is an ln of something to a power, so I can use the power rule or plug that x back to the front. So I can move the exponent into the front of the ln expression. So now that allows me to solve for x because ln of 4 is just a number. So I can divide it, just like this was 4x, I could divide by 4. It's the ln of 4, so I can divide by the ln of 4. So x is equal to the ln of 15 divided by the ln of 4. Awesome. Your calculator does the work. That's 1.95, about. So let's take a look at this one. Why don't you try this one? It's going to be very similar. go ahead and pause the video, and I'll be back to check your steps and work when you're done. Glad that you're back. All right, so let's check that workout. ln both sides, just like we did with the first example. Reverse power rule, or plug that for the win. So I get x ln of 5, divide both sides, and your calculator does the heavy lifting. Did you get 3.04? You followed those steps, I bet you did. Sweet. All right, so let's put it all together. I'm getting excited. All right, so this example is a little bit more intense. We got a coefficient. We have the e to the 2x. So again, of course, right now I know that my variable is in the exponent. So that's awesome. I know I have tools to move that variable. I'm just going to have to isolate e to the 2x. So each of the steps that you're going to see me do now is to isolate e to the 2x. So move that 5 using the inverse operation. I'm going to see that 7 is a coefficient of the term that I want to isolate. So to isolate that, I'm going to divide. That leaves me with e to the 2x is equal to 9. Awesome. This is simple now. ln both sides. And here's the thing. Now that we use the ln, or the natural logarithm, the best part is I have ln of e to the exponent, which you recall ln of e to whatever simplifies to that exponent. So that lets me say that 2x is equal to 9. Well, if 2x is equal to 9, evidently ESPN is also excited, then I can divide to isolate x, and yes, x is equal to the ln of 9 divided by 2, or 1.01. Evidently top play material. Another example. Here we have this one. This is going to be some heavy lifting here. You see I have different bases, so I'm going to have to take the natural logarithm of both sides. Now I'm going to have to reverse power rule here, and when I reverse power rule, that's going to allow me to take the exponents, which are now binomials, to the front of the natural logarithm. Now, this might look more complicated, and yes, it will look more complicated before you get simple and solve for x. The key part here is that the ln of 3 and the ln of 7 are only numbers. So if this was 2x minus 1 times 3, I would distribute. Or x plus 1 times 7, I would distribute. In the same way, in the next line of work, you see that I've distributed. ln of 3 times 2x is 2x ln of 3. ln of 3 times negative 1 is just negative ln of 3, or minus the ln of 3. In the same way, I've simplified the right-hand side of the equation by distributing ln of 7, which again is just a number. All right, so moving on, this lets me isolate all of my variables on the left-hand side of the equation and all of my constants on the right-hand side of the equation. So this gives me a very complex expression, but again, it's starting to get simpler because the variables are on one side and all of the constants are on the other. So 2x ln of 3 minus x ln of 7. Now that is awesome because I have x with each of these terms. Anytime I have x with each term, I can use my favorite math F word, factor. And I'm going to factor the x out, which allows me to get 2 ln of 3 minus ln of 7. Now that's just a number. And if it's just a number, then I can actually just divide to isolate what x is. Awesome. So now I just divide both sides by 2 ln of 3 minus ln of 7, and x is equal to this complex fraction. Now, yes, I could put that in my calculator. So could you. We could find out what that equals. 12 plus, or 12.11, not plus, 12 and 11 hundredths. That is awesome. Okay, so this second example is important. There are several homework problems that deal with it, and it is a deep and awesome look at using the natural logarithm to isolate variables that are located on both sides of the equation, and in each instance in the exponent. All right, so let's move on. All right, let's work this one out together. Okay, checkpoint 5. So, I see something weird here. I see e to the 2x and e to the x. Now, if that was something different, it would be a quadratic equation. So let's use substitution. And I see that if I make u equal to e to the x, and that makes u squared e to the 2x. that means I can rewrite that green equation with the exponent and e as a quadratic equation, which I can factor using the x, which allows me to rewrite the equation and solve for u. Now again, I get the coefficient of u squared is 1. 1 times 7 is 7, which is the top number. B is negative 8, and negative 1 and negative 7 multiply to positive 7 and add up to negative 8. So powerful substitution, because now I can solve for u. U is equal to 1 and u is equal to 7. That allows me to put u equals e to the x back in, so reverse substitute, and solve. E to the x is equal to 1 and e to the x is equal to 7. Now, if that was my two problems, whoa man, just use the natural logarithm and we're done. So that's why we use the substitution, or this purple line here. All right, like I said, we're going to work this one out together, and it's going to put together a lot of topics that we've been looking at so far. So take the natural logarithm of both sides. We know ln of e to the x is equal to just x. X is equal to the ln of 1. X is equal to the ln of 7. And what? A logarithm, or any logarithm to the 1, or ln of 1, or log of 1, is just going to be 0. Awesome. X is equal to 0 and ln of 7. Well, that's some awesome work. We put together things from our first exploration together all the way up here to using the natural logarithm to solve exponential equations. Whew. Exciting times, guys. So you try these. All right, so I'm going to pause the video, or you can pause the video. I'm going to actually just work out example number 1, and then I'll give you a chance to pause the video again and work out example 2. So I'll stop talking, and you can pause the video to work out the first example on your own. Glad that you're back. Here we go. 5 to the x minus 1 over 3 is equal to 5 to the 1/3. Yes, I can rewrite this as a rational exponent. That just means I can set them equal to each other. Multiply by 3 to get rid of that denominator. Kaboom! I have x minus 1 is equal to 1. X equals 2. All right, you can pause the video and check out your work and answer for number 2. Now that you're back, we substituted u is equal to 3x, which means u squared is equal to 3 to the 2x. Yes, that means you can factor, solve for u, and then reverse substitute back in to get u is equal to 3x, and then we have 3x is equal to 5, and 3x is equal to negative 6. We take the ln of both. Now this makes me feel real awkward, because I know I can't take the ln of negative numbers. The domain for the logarithmic function must be greater than 0. Therefore, this is not a solution. So I can just chop this one right off. But this one, I use the power rule, bring the x up to the front, some simple division, calculator work, x is equal to 1.46. That was awesome. All right, so let's solve some logarithmic equations now. So if we're solving some logarithmic equations, we got some ground rules. First, you got to check your solutions. Yeah, you got to remember that the domain of a log, or a logarithmic is greater than 0. You saw that in our very last slide here when I saw that I could not accept this as a solution. So remember that the domain of a logarithmic function must be greater than 0. And here's our first example. All right. Now, this looks like I can't do anything to it, but I can actually use a definition of logarithms to rewrite this as an exponential function. 2 to the 3rd is equal to x minus 4. What? 2 to the 3rd is just 8. And that means I can use the inverse, and I can add 4 to both sides. 12 is equal to x. All right, not done. Remember the ground rules here. We got to check the solution. So we're going to check. I'm going to plug that 12 back into my original equation. So the 2 log of 12 minus 4 is equal to 3. Well, I know 12 minus 4 is 8. What? The 2 log of 8 is equal to 3. If we rewrite that as an exponent, we know that is true. So x does equal 12. All right, let's look at another example. I got 4 ln of 3x is equal to 8. So let's isolate that logarithmic by dividing each side by 4. All right. Now remember that the ln is just the base e log. So I can say e to the second power is equal to 3x. So I'm just using the definition of logarithms here and the knowledge that ln is the base e logarithm. So that's where I get this e from. It didn't just magically appear. And I can solve for x, but we're not done. Gotta check. So if we check, we're going to plug it back into the original equation up here. So instead of 3 times x, we have 3 times our proposed solution. So when I multiply, these are going to cancel. I've divided both sides by 4. So the ln of e squared is equal to 2. Well, ln of e to an exponent is just that exponent. So yes, 2 does equal 2. This checks. Boom! E squared over 3 does equal x. All right, some powerful stuff happening here with solving logarithmic equations. Remember, we need to check our solutions now. So let's put it all together. All right. Now these are both logs, base 10 logs. I know I'm adding, so I got to condense this. If I'm adding logarithms, that means I can condense it using multiplication. I can distribute this x. And now I can rewrite this logarithm as an exponent and, in a sense, get rid of the log. So the base here is 10, because we know that if there is no base, the base is 10. So I have 10 to the first power is equal to x squared minus 3x. Well, I'm going to move that 10 to the other side. This gives me a quadratic. I can factor and solve this quadratic. Yes, negative 5 and positive 2 multiply to negative 10 and add up to negative 3. All right, here's where it gets awesome. I got to check them. So I'm going to put it back in. Let's see, x is equal to negative 5. So I'm going to just put in 5, to the original logarithmic function. I get log 2 because I have 5 minus 3 is 2. If I'm adding, I can multiply these logs, which means the 5 times 2 is 10. And the log of 10 is equal to 1. Yeah, it is. So let's check negative 2. Red flag, we cannot find the log of negative numbers. It's not in the domain of a logarithmic function. So x is just equal to 5. Sweet. We've put it all together. We've condensed logarithms, and that allows us to rewrite a logarithm as an exponential expression. Once we've done that, we just use factoring and then to check our work by plugging it back into the logarithmic function. This is exciting work. All right, let's take a look to the next level. All right, yes, this is like the last level that I can take it to. It's okay, I know. Tray tables in their upright position and seat belts locked and fastened. Here we go. Checkpoint 8. ln of x minus 3 is equal to ln of 7x minus 23 minus the ln of x plus 1. That's a mouthful, but I see subtraction, which means that I can actually combine these two logarithms as a division problem. Now this is unique. We have not run into this yet, and I have two ln's. What am I going to do? So I'm going to actually make these, and remember, whatever I do to one side, I can do to the other. So I'm going to literally make both of these logarithms the exponent of base e. In so doing, I know that e to the ln of something is equal to just that. In fact, now we have the same base, and we can get rid of, in one fell swoop, the natural logarithm. And that leaves me with just the exponents here. X minus 3 is equal to 7x minus 23 divided by x plus 1. I know. Huge leaps here. But the biggest part here is to know that what we do to one side, we can do to the other. So I can make the base e and the ln functions into exponents. So powerful. Now I can just multiply to cancel out the x plus 1 in the denominator. That leaves me with two binomials. I can FOIL the left-hand side, move the x's to one side. Oh, I can move everything, make it equal to 0. I can factor that. That allows me to actually find out that x is equal to 4 or 5, which means I can check both 4 and 5. Let's check 4 back in the original equation. 4 minus 3 is 1. That's the ln of 1. If I put 4 here, I have the ln of 5. What? Hold on. I know the ln of 1 is 0. And here on the right-hand side, we can obviously see ln of 5 minus ln of 5 is 0. This checks. 4 is a solution. So we got to check 5. So I'm going to put 5 back in my original equation. Pause the video and see if you get the same answer that I do. You should have ln of 2 is equal to ln of 12 minus the ln of 6. Please do not be tempted just to subtract these. That's not what we're doing. Remember, when you subtract logarithms, you can make it into it's a division problem. So it's 12 divided by 6, it's 2. That's how I know that the x equals 4 and x equals 5 are both solutions to checkpoint 8. We have literally put together everything. It's all starting to flow together in a cohesive kind of a toolbox here to solve some of these more complicated problems. All right, two for the road. You have the tools to simplify both of these. So go ahead and pause the video. I'll give you a second to do that, and I'll walk through the solution after you've tried to work it out on your own. I know that you can do it. Yes, you can. A sip of tea later, I'm back, and here we are. We're going to condense the first part. So we have x minus 3 over x plus 3. We're going to raise them both into exponents with e as the base. I'm going to cancel here by multiplying times both of the denominators. This is frequently a spot that I see students get stuck in. But this cancels, so the x plus 3 cancels, leaving me with x times x minus 3. And the x's cancel, leaving me with 2 times x plus 3. Okay, so now I can start distributing, moving everything over to one side. Factor. This lets me solve for x, and I know that the natural log cannot have negative numbers in its domain, so I can immediately reject x is equal to -1. And that's primarily because if I take this -1 and plug it into the very first natural log here, I get -1 minus 3, which is negative. Does not work. So I can immediately reject that one. I can check 6 though. By plugging 6 back into our original function, here's what we get. Now remember, when I subtract logarithms, it's just division. So I can rewrite that as a fraction. 2 over 6 does simplify to 1/3, and 3 over 9 also simplifies to 1/3. ln of 1/3 must be equal to 1/3. This checks. X equals 6 is my answer. Whew. First one down. Second one left. Pause the video, check to see if you can do the work on your own. Awesome. So if we're adding, that means we're multiplying these two binomials. Glad that you're back. And that lets me FOIL these. And then after I've FOILed, I can actually just use the definition of logarithms. So 4 to the first power is equal to this. So x squared minus x minus 2, which is what this FOILs to. Which is awesome, because now I can just move the 4 to the other side, and you guessed it, factor, solve for x, and immediately reject the logarithm of negative numbers. This -2, when I plug it here, will give me a negative number, so that does not work. And then I can check x equals 3. If I put 3 here, I get this expression. If I'm adding logarithms, again, I can multiply, so 4 times 1 is 4. This absolutely checks. The 4 log of 4 does equal 1. X is equal to 3. Ladies and gentlemen, this was our first marathon session. Hopefully we don't have another one that goes over 23 minutes. But you've done it. We have solved exponential and logarithmic equations. We've reached the end. I know that you're going to rewatch this video. I am excited for you to get into these problems. They are just full of putting together everything that we've done so far. And it's a great way just to touch base with yourself and see if you can kind of see how we're simplifying just one little bit at a time. I'm excited. I know that you are too. I'm going to let you get to work.